All right, we're moving on to chapter 15. Chapter 15 deals with Chem 1B style stoichiometry, which is different than Chem 1A style stoichiometry. In Chem 1A, we look at reactions that have strong driving force. That is, let's take a look at one of these acids here, like HF. Example. If we have HF, it's a moderately weak acid here, and we react it with like hydroxide, what we see is this is a highly favorable reaction. That is, this is steep downhill run to hydroxide, and then what forms here is a much weaker acid. So we go from HF hydroxide to H2O. When we compare the strength of HF versus H2O, H2O is a much weaker acid being much more stable. And then we form fluoride. Fluoride is a much weaker base than hydroxide, so that's much more stable as well. And so here we're going from unstable reactants to more stable products. That's very favorable as far as driving force goes. And so the stoichiometry works out. If I have 1 mole of HF reacting with 1 mole of hydroxide, then I'm going to form 1 mole of fluoride and 1 mole of water. It's just standard stoichiometry. But what if I have something like HF reacting with this, formate? Then this isn't as steep here. And the driving force is going to be much less significant. And so what may happen is this. So if we have HF reacting with hydroxide, then that's going to be a highly favorable reaction. And the products it produces will be fluoride and water. If I look at HF reacting with something like formate, which is HCl minus, HCl minus, then what I form here is fluoride and this one, which will be formic acid, HCOOH. Okay, so this one's going to have a very large driving force. Driving force DF. And this one will have a much smaller driving force.
To create formic acid?
Yeah. If I do the whole reaction, like that. So I'm going to have HF plus HCOO minus. And this is going to go downhill to F minus plus HCOOH. So it's a Bronsted acid-base reaction. In a Bronsted acid-base reaction, we have a proton transfer from the acid to the base. And so here, the proton is leaving the HF and going to the HCO minus. And so the names, you don't have to know the name of this. This name of this one is formate. The name for this one is formic acid. And so we're going from formate to formic acid. Let's compare that to this one, the alternative reaction here. Alternative reaction would be still HF and hydroxide. Do that over here. If we start off with HF plus hydroxide, hydroxide is a much more powerful base. And this is going to be a large driving force here, downhill. And the products of this reaction are much more stable. Stability is related to the bonds. If you have stronger bonds, it's more stable, less reactive. And so in this case, we're going to have proton transfer, so we're going to have the fluoride and H2O. And so this is what we call downhill here. And this line isn't as far downhill here. Now, in the situation with something like this is this. This is thermodynamics. So what we have here is enthalpy, usually, or energy on the axis here. Different symbols. Now, a reaction like this here, we could just do our standard stoichiometry, and that is HF plus hydroxide yields fluoride plus H2O liquid. And so if I had 1 mole of HF reacting with 1 mole of hydroxide, I'm going to form 1 mole of fluoride and 1 mole of water. And so this is just our standard stoichiometry. If I had 2 moles of HF, I'm going to get, depending on what the limiting reagent is, 2 moles with excess hydroxide, I'm going to get 2 moles of fluoride. Now, over here, I have my HF plus HCOO minus. This is going to go to F minus plus HCOOH. Now, when I do this one, what happens is, if I start off with 1 mole of HF and 1 mole of formate, what do I predict? Stoichiometrically, I predict, well, it's a reaction 1-1 mole ratio. So this is stoichiometric mixture, and so I expect to form 1 mole of fluoride and 1 mole of water, not water, but in this case, formic acid. So this is based on stoichiometry here. But when I do this reaction, and I wait for this reaction to go to completion, it never does. This reaction will not go all the way to the end. And the reason it will not go to the end is because of this. There's a significant amount of reverse reaction that can occur here. And the significant amount of reverse reaction is this. So this is downhill. And so I'm going to make these. But at 25 degrees C, we have to look at the kinetic energy. When we look at this, this is what we call potential energy. But kinetic energy is energy of motion. Right? And so at 25 degrees C, we see a distribution of kinetic energies. We'll put KE for kinetic energy, or E sub K. And then over here on the y-axis, we'll put population. And so it turns out here that at 25 degrees C, not everybody has the same energy. We see a distribution of energies. And this distribution of energies, distribution of kinetic energies, means that, the fluoride and the formic acid will have this distribution, and this distribution of kinetic energies is called the Maxwell-Boltzmann distribution. Or thermal distribution. I missed an N on Boltzmann. You probably recognize this from the speed distribution for gas molecules. It's like this. This is at a given temperature. So you got gas at 25 degrees C. Most of the gas molecules are here. There's going to be a small fraction of high energy and a small fraction of low energy. Both of them are going to span this range here. If we change the temperature, that changes things here. And so we have different things: most probable speed, average speed, root mean square speed. Speed is related to kinetic energy. If we increase the temperature, it shifts the distribution here. T1 would be at a lower temperature, T2 would be at a higher temperature. If the population stays the same, then the area under the curve is the same. It just shifts it to higher energy. So what happens is this. If we look at the fluoride and the formic acid here at 25 degrees C, there's going to be a small population that's going to have fairly high energy. We'll have a cutoff here. So let's say this is the cutoff energy here. What can happen here is if you have a population of this, the small population of that will have enough energy to make it back up the hill. How can you prevent these from going back up the hill? The only way you can prevent these from going back up the hill is to you can't. You can't prevent these because they're going to collide, and sometimes when they collide, they're going to collide with enough energy to make it back up. And so this is what we call a two-way reaction. That is, yes, downhill. Most of them will go downhill, but then there's going to be this population that will refuse to stay downhill. And this population can grow significant so that we get significant reverse reaction occur. Yeah. And so we can see that. And it depends on how much, how big of a hill it is. If it's not such a big hill, that population can be quite big. Yeah. Or bigger. It depends on how much energy it requires to get back up the hill. Now, the only way you can prevent this from occurring, the reverse reaction, is to completely freeze it so that there's no kinetic energy, there's no motion. And so if we froze everything so that they can't move, then yeah, we can get it. But if we're at 25 degrees C, then we can't avoid it.
So the reverse reaction is like when the product goes back to its
Yeah, so what's going to happen is you're going to get a violent collision. It's going to roll back uphill. This is not the favored direction, but if there's a violent collision, you can break off. And we get these. And then eventually this is going to roll back down. And so we're going to have some going up and some going down at the same time. Eventually we're going to reach a point where the rate of reverse reaction, the rate of going up, is equal to the rate of going down. And when the rate of going up and the rate of going down are equal, then no more change happens. So that's the end of the reaction. We can wait forever for this to go to completion, but it's never going to go to completion because we're going to get this constant upsurge. And the reaction is going to stop when those rolling down and those rolling up are equal. That's what we call equilibrium. Now, something like this, it doesn't take that much energy to make it back up the hill. So really, it's probably, somewhere like this, where we got a larger population that can make it back up the hill. In fact, it depends on, this. Whereas something like this, if you're down here, how many can make it all the way back up this cliff, the climb? And here, the population that has enough energy to make it up there is going to be probably minuscule. So if we looked at the same Maxwell-Boltzmann distribution, Boltzmann was with two ends. And we looked at the fraction that can make it, because it's such a high energy, and this high energy is far to the right. And as we go further and further to the right, the population gets thinner and thinner, so that there are very few that can react back up the hill. So this is pretty much a one-way reaction because it's too difficult to make it up. And so in Chem 1A, we do this, this type of reaction where we don't have to worry about backwards reaction occurring. just do. Okay, likewise, if we had something like this, let's say we had HF, and in this case, we're going to react it with like nitrate. Let me just do, sorry, I'll do one thing here. So if I have HF and nitrate is a very poor base. Okay? And if I try to get these two to react, the products for this are going to be steeply uphill. That is, the products of this would be F minus and HNO3. And so when I think about this, there is basically no driving. This is not a downhill, so there's no driving force, so we expect no reaction. No reaction. NR just stands for no reaction. Okay. And so in Chem 1A, you know, this kind of stoichiometry, we just say that no reaction, therefore nothing's going to happen. For this next example here, let's take a look at HF, and rather than nitrate, we'll try nitrite. Now, nitrite is a significantly stronger base than nitrate. And so nitrite actually has a pretty good attraction for H+. And so if we do HF and nitrite here, what we expect is we expect F minus and HNO2. Well, HNO2 is a little stronger, you know. HNO2 is a little bit stronger than HF. And so it's not favorable. We're going from a weaker acid, which is more stable, to a stronger acid. Just the same thing here. We're going from a weaker acid, HF, to a stronger acid, HNO3. That's not favorable. That's not the downhill direction, that's the uphill direction. We look at this now, it's the same thing. We're going from a weaker acid to a stronger acid. This is the uphill direction. But in this case, should we say, well, again, should we say no driving force, no reaction? You know, are these two the same? No driving force, no reaction. Well, what we know about kinetic energy distribution, the Maxwell-Boltzmann distribution, is this. This is the uphill direction, for sure. This is the uphill direction. So most of them won't want to make it up here. They'll just want to stay down here. And so, again, this is population on the y-axis. And then on the x-axis, we have energy, kinetic energy, KE. Over here, when we look at this case, you know, the amount of kinetic energy that it's going to take to climb up the hill is going to be kind of insurmountable, basically. This. So the kinetic energy cutoff for this one is like way out here. And so there's pretty much zero population that's going to make it up the hill or close to it. However, the kinetic energy cutoff for this one, which we'll call 2, is more achievable here. And so we might have something like this. So the bulk of it will stay no reaction because, it's going uphill, not downhill. But there's going to be a fraction here that's going to have sufficient energy to make it up. And this fraction will be given by this population here under the curve. So if we were to say that there's no reaction here, well, that's wrong. There's partial reaction here. And so we have partial reaction. And so this is wrong. We expect partial reaction. Here, this is for the most part correct. We don't expect much reaction to occur. So the next question comes out, well, how much reaction should we expect here? Can we quantitate it? Because we want to be quantitative. We want to know how much. That's what stoichiometry is all about. How much? How much product are you going to form? What's the theoretical yield? And so we need to figure out how to be, for these partial reactions, we need to figure out, and we can treat all reactions as partial reactions because maybe there is one out of a billion that can make it up this, We'd like to know, if I had 1 trillion, is there a couple that can make it up this or 0? Maybe trillion's not, maybe I'd be like 100 million trillion. If I had 100 million trillion population, could I have 2 that can make it up? And so those are the types of things we'd like to know, even for these, even for Chem 1A style. And the same thing goes here. If I had 100 million trillion, will they all be down here, or will there be 1 or 2 that can rebel against that, make it up? And so Chem 1B stoichiometry wants to find out, how much. If we have partial reaction, how much occurs. And so let's take a look at some Chem 1B stoichiometry here next. I'm going to present it a little bit differently than the book does. I'm going to present it more from historical perspective. All right, let's take a look at this reaction here. The 2 copper 2s in the blue, tin 2. This is a redox reaction. So we have copper 2 going to copper 1 and tin 2 going to tin 4. So there's some electrons that are being lost and electrons being gained in this particular reaction. So what we're going to do is we're going to look at this experiment 1 data first. Here. If we look at the experiment 1 data here, we start off with 0.1 molar or 0.100 molar. 0.100 molar copper 2 and 0.100 molar tin 2. If it were a liter, that would be 0.100 moles of copper 2 and 0.100 moles of copper 1. And normally we talk about moles, so let's go ahead and say we have 1 liter of solution. So if I had 0.100 moles of copper 2 and 0.100 moles of tin 2, which one would be the limiting reagent? So if I had 0.100 moles of tin 2, then I need twice as much copper. And so if I had 0.100 moles of tin 2, I'd need 0.200 moles of copper, but I don't have it. I just have 0.100. And so the limiting reagent is going to be copper 2. It's a limiting reagent. And that means all the limiting reagents consumed. And so what we predict for stoichiometry is if I had 0.100 moles, 0.100 moles, this is a limiting reagent that's going to be consumed. So I'm going to form 0.100 moles of copper 1, and I'm going to consume 0.05 moles of tin 2. That would be Chem 1B stoichiometry, but it turns out that copper 2 and tin 2, let's take a look at copper 2 and tin 2 here. It turns out that copper 2 and tin 2 is that a very steep downhill? That's favorable, right? Is that very steep downhill? No. This isn't. And so if it's not that steep, even though this is a favorable, it's a downhill, we're going to form, actually we're going to form copper, we're going to form, this is not, we go to copper 1, sorry, we can't use this chart, we have to use a different chart, but nonetheless, it's not that steep downhill. And if it's not that steep downhill, what that means is we have the potential for reverse reaction occurring, even though it's favorable, the reverse reaction can occur. If the reverse reaction occurs, then we aren't going to go completely to product. And so this is what's observed. Okay, now we can use molarity as well as moles, so we're going to use molarity here, 0.100 molar, 0.100 molar, 0 molar, 0 molar for this. What we expect is all the copper 2 should react. So the copper 2 should go to 0, and the tin 2 will consume half of it. And so this will go to 0.050. But what we see is that not all the copper 2 reacted. So what they did was they took the initial, and then they figured out at the end of this, that is, once we reach a state of equilibrium, nothing's changing anymore at the macroscopic level. And so once we hit the state of equilibrium, what we observe is this. We observe about 36% of this unreacted. That is, we didn't consume all of it. We consumed 64%. They pick numbers like this so you can figure out the percentage. If this is 100, this is 36. So that's 36% left. That means the change here was 64% consumed. And so we didn't consume all the limiting reactant. Why is that? Because, this is never going to go to completion. What's going to happen is there's going to be a population of the product that's going to go back uphill, that are going to refuse to react completely. And so this is what's observed. And so what we can say is this. What we can say is that this reaction has 64%. Do you see that 64% reaction? That's what we observe. Okay, so let's go on to experiment 2. If we go on to experiment 2, we're going to start, this is downhill, right? So we're just going to start downhill here. The whole population is now downhill. In other words, it's all product. And then what we're going to try to figure out is how much of that population can make it back up the hill. And so in this case, it looks like 36% of the population remained up the hill. Does this make sense, or do I need to draw this out? And so what do we expect? Well, I expect 36% of the copper will make it back uphill, and 64% of the copper will stay downhill of the product here, right? 64% will stay downhill, 36% will make it back uphill. Will you agree? Okay. So we do that, and then we go ahead and let it react, see how much of the population can make it back up the hill. And take a look at what happens here. When we look at it, here, 56.7% of the population made it back up the hill. 56.7%, maybe 56.7%, maybe I'm getting it wrong. Which direction is downhill, which one direction is uphill now? Because this one went downhill, 64% went downhill, 34% remained uphill, right? When I look at this one now, I'm starting with everybody downhill and seeing how many can make it back up the hill. And it makes sense to predict 34% would make it, or 36% would make it back up the hill. But in this case, we have even more, 56.7% make it. And that means only 43.3% remain downhill. But if that's the case, then I have it backwards. Or there's something very confusing about this, because the numbers don't make sense. Okay, so we try a different experiment. And we start off with equal populations on both sides, uphill and downhill, and see what happens. If we start off with equal populations all throughout, then which side gained, which side lost? Looks like the right side gained, do you see that? And the left side lost. So it looks like the right side is downhill because that's going to gain, that's favorable. Going downhill is favorable, going uphill is not favorable. And so it looks like the right side is downhill, the left side's uphill. But how many went downhill? So if we started with 100, which is the limiting reagent here, how many did we lose? We went from 100 to 92.2, which is losing 7.8%. So we lose 7.8%, and we gain 7.8%. So the point of this is, the percentages don't make sense, right? It's the same reaction, but it's coming up with different percentages. So these are our observations. So in the scientific method, first we take our observations, and then what do we do? We look for patterns and trends. We try to analyze the data here, right? And do you see any pattern? Well, I was trying to look for a pattern, the percent reaction, but the percent reaction is not a pattern that's observed here. And so let's try what we commonly do in science. What we commonly do in science is to graph it and then look for a pattern. So here's the first experiment. The first experiment is where we have, the 64% reaction here, the copper. Let's see which one's the copper. This magenta. And so in this first reaction, we start off with 0.100 the magenta, and we have 64% of it react. And what we're left with is 34% remaining unreacted at the top of the hill. The rest is converted into the blue here, which is the black here, the black here, which is the copper plus. And so we're looking for the pattern. It goes blue, black, magenta, green. Do we see the same pattern here? Well, looking at the pattern here, it looks like inverted, blue, black, magenta, green. Okay, let's look at, this is the second experiment. For the third experiment, do you see a pattern there? Well, it looks like green, black, blue, magenta. So is there some consistent pattern that, no.
For the second experiment, you said that was how many percent?
54, 55%, whatever, it's different than the first.
Right.
And so we can't use it. And the third was yet a different. In fact, if we did a fourth, starting with different, it'd come out different again. Each time you do this with different concentrations, it comes out different. If you did it with the same concentration, let's say we repeat experiment 1, then we get the same, 64%. And so what we're trying to do is we're trying to see if there's a pattern there that we can figure out. And so that didn't work graphically, but maybe we could try numbers here. And so they tried lots of different mathematical combinations of these numbers to see. And so, for example, after spending a lot of time, they took, is there a ratio to this? You know, so if I look at the end of the reaction, let's take the products over the reactants. Is there a ratio that's consistent for all three? And so if I take the products over the reactants, no, there's no ratio. There's no agreement with the numbers. We get different ratios. Then they tried different things. They tried the products and then multiply. So for example, here we have copper plus, so maybe we double this. And over here, with the copper 2 plus, we have 2, so maybe we double that. So we doubled the copper concentrations and then took the ratio. Is there a pattern there? And the answer is no, there's no pattern there either. And then finally somebody did this. Well, we're not going to double the copper, we're going to square it. So if we take the copper squared, you know, there's no pattern in the initial, because initials, you could start off with whatever we want, but at the end of this, is there a pattern? And so at the end of this, if we take the copper at the end, and the tin at the end, and the copper 2 at the end, and the tin 2 at the end, and then square the coppers, then is there a pattern? Well, let's see. So if they did that, they got 1.49. Again, there's no pattern in initial because the initials are starting at different conditions, but at the end, is there a pattern? And so in experiment 2, they did the same thing. They square the copper concentrations and they take the product over the reactants and they got 1.48. Well, 1.49, 1.48 are close. And so maybe there is a pattern there. And then they go on to experiment 3 and then see. You know, the initial for sure is way different. The initials from all these are different. But at the end, take a look at where it ends up at. And so even though we started at very different initials, they all came to about the same ending. And the same ending is about 1.48. And so what this means is there's a pattern. Now that pattern can evolve into what? Patterns can evolve into, what's the next step of the scientific method? Laws. Patterns can evolve into laws. And so this would be this. The law of equilibrium. The law of equilibrium is going to look like this. We try this pattern on a whole bunch of different reactions. And so we'll just take a generic reaction. This is a generic reaction. Little a is the coefficient, a is the reactant, little b is the coefficient, big B is the reactant, plus however many reactants there are. And this is going to be two-way, you know. Some can make it uphills, you know. So this is going to be two-way. This is going to go to G plus H plus ... These are the products. And the consistent pattern that we see when the reaction ends, that is this. It's called KEQ. EQ stands for equilibrium. Equilibrium is going to be the ratio of products over reactants. And we have different KEQs. One of the KEQs is if we express these as concentrations. If we express these as concentrations, then this C stands for molar concentration. Then what we get is the concentration of G, which is the first product there, raised to the little g power, H raised to the little h power, ... over A raised to the little a power, B raised to the little b power, ... It's going to go crank. Now, lots of different things were done. This is a little bit weird because we're talking in terms of molarity. Normally when we do stoichiometry using a balanced chemical equation, it's mole ratio, not molarity ratio usually. And so up here, it's like 2 moles of copper 2, 1 mole of tin 2, yields 2 moles of copper 1, and 1 mole of tin 4. And so let's note here, note, K in terms of moles is not a consistent pattern. That is, you get moles of G raised to the little g power, moles of H raised to the little h power. I'll use N for moles. Over moles of A raised to the little a, moles of B raised to the little b. This doesn't work. This does not work all the time. It only works if we have a special case. So I'm going to say this does not work. It only works if the volumes cancel out. That is, if I'm looking at molarity and the liters will cancel out. It only works if the molarity, the total molarity on the left is equal to the total molarity on the right. Of the reactants is equal to the total molarity of the product. And the volume, and thus the volume cancels. So what I mean by this is this. Let's say I had this G to the first and H to the first. And so that would be molar squared. And then let's say I had A to the first, B to the first. That would be molar squared. Molar squared would be moles per liter quantity squared, moles per liter quantity squared. And so in that case, the liters will cancel. The moles will be different because we're looking at different things, but the liters will cancel. However, if I had, let's say, molar cubed on the top and molar squared on the bottom, then the liters don't cancel because I'd end up with liters on the top. And so using moles, we don't get the consistent pattern. They tried it. They tried taking the mole ratio. The mole ratio failed, the ratio of the products to the reactants. They tried lots of different things. And so it has to be molarity. Or there's one other thing. If we're dealing with gases, gases can be expressed in terms of molarity or pressures. And so for gases, we have something called Kp. Kp is just equal to partial pressure of G raised to little g, partial pressure of H raised to little h, dot, dot, dot. And then on the bottom, partial pressure of A raised to little a, partial pressure of B raised to little b, dot, dot, dot. So Kc we use for solutions and gases. Kp we use for gases only. Solutions aren't going to be exerting partial pressures. And they're related. So let's say I have gases, I can use either Kc or Kp. Kc and Kp may or may not be the same. And so let's look at the relationship between Kc and Kp. But before I do that, let me just say that knowing what the ratio is going to be at the end means this. We normally set up Chem 1B stoichiometry using an ICE table, ICE. I stands for initial. So whatever we have initial, we want to figure out, given this initial, how much reaction am I going to get? And then C is a change. The change wasn't shown here. I just calculated the change in my head. So if I started off with initial 100 and I end up at 36, then that's a 4% change. You know? And so here, we can see, if I start off at 0, I'm going to end up with 64% change since the coppers are the same. And then E is the end of the reaction, or equilibrium. Nothing's going to happen after this. EQ, equilibrium. And so if I know what we're targeting at the end, then I can figure out, you know, the changes, because I got to get that right ratio, the right ratio of product to reactants. You know? And so for the previous example, no matter what I start off with here, I need to end up at about 1.49, 1.48. That's the right ratio. 1.48, if I average those three, is what I want. And so KC is going to be important. KP is important. We can interchange between KC and KP by doing this. Talk about that here. The relationship between KC and KP, or KP and KC. For gases. If I have an ideal gas, then we know that the pressure is equal to nRT over V. N over V is moles per liter. Moles per liter is the molarity. So I'll give the symbol M. And so P is equal to the molarity times R times T divided by P. Actually, it's MRT. That's it. Molarity times R times T. And so let's take a look at substituting here. Molarity is just the concentration. Concentration, I usually use square brackets for the molar concentration. And so let's take a look at the Kp over here. Kp is equal to partial pressure of G raised to little g. Partial pressure of G is equal to molarity of G times R times T. Molarity of G is just square brackets G times RT. So this would be the partial pressure, and then I raise this whole thing to little g. So this is partial pressure of G. Molarity of G times RT. Then the partial pressure of H is going to equal the molarity of H times RT raised to little h, dot, 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 divided by the molarity of A times RT raised to little a, B times RT raised to little b, dot, dot, dot. We have something like that. And then what I'm going to do is I'm going to factor out the RT. If I factor out the RT, I'm going to get G, little g, H, little h, over A, little a, B, little b, the concentrations, times RT. And when I have these exponentials here, I add them. So this would be RT to the G plus H plus whatever. So it's going to be RT raised to the G plus H plus dot, dot, dot. And then I subtract these ones. So that's going to be minus A plus B plus dot, dot, dot. So it's going to be RT raised to that power. Okay, in other words, it's going to be the total moles of product gas minus the total moles of reactant gas. What we call that is, we call that delta N of gas. This one is just Kc. It's just the concentration. So this is Kc RT to raise to the delta N of gas, where gas, delta N of gas is the total number of moles of product, gas minus the total number of moles of reactant gas. If we have the same number of moles of gas on the reactant and the product side, then delta N of gas is 0. If delta N of gas is 0, then Kc and Kp are equal. So if delta N of gas is 0, that is, there's no change in the number of moles of gas going from reactant to product, then Kc is numerically equal to Kp. So number. On the other hand, if there is a change in the moles of gas, then numerically they're going to be different. And so we'll make sure for gases, we use the atmospheres of the bar. For solutions, we use molarity. All right, then this comes next. What if we have other things in there, like pure solids and pure liquids? For pure solids and liquids, concentrations and pressures do not change. Maybe I should say concentration. Actually, is there pressure for liquids? No. In fact, when I think about it, solids, there's no pressure for gases. There's small vapor pressure for solids and liquids. We learn about the vapor pressure of liquid, right? Some liquids are more volatile than others, but we're not going to. We're just going to say concentration does not change. So what do I mean by this? I mean, if you have a liter of water, do you know what the concentration of water is? If you have a liter of water, how many grams is that? A liter of water is 1,000 milliliters, which would be about 1,000 grams. So you have 1,000 grams. Do you know how many moles 1,000 grams is? The molar mass of water is 18 grams per mole. So it works out to 55.5 moles. So you have 55.5 moles of water in a liter of water. This is pure. So that we call 100% pure water. What if you have 2 liters of water? Is it twice the concentration? Is it 200% pure? Is there such thing as 200% pure? No. It's still going to be 100% pure water. What if you had, let's half a liter? Is it half as pure now? No, it's still 100% water. So concentration does not change. And so if the concentration does not change, what we do is we ignore. And the same thing goes with the pure solid. You know, if you have pure sugar, you know, it doesn't matter how many grams, 10 grams, a kilogram, a microgram. If it's pure sugar, it's the same concentration regardless. And so pure solids and liquids, concentration does not change. Ignore these in the cave. And so ignore, that is omit these from the K expression. So we don't include those. What if we have a mix of solution and gas? What should you use? Well, for solutions, we're supposed to use Kc. For gases, we can use Kc or Kp. And so if you have a mix, it seems like the only thing you can do is Kc, but it turns out if we have a heterogeneous mix, then we should use that KEQ. KEQ is going to equal the concentrations if solution or pressures if gas. And so if we're looking at something like this, calcium carbonate, solid, HCl, this is going to go to 2 HCl. This is going to go to H2O plus CO2 plus calcium chloride. H2O is a pure liquid. CO2 is a pure gas. Calcium chloride is a solution. And calcium carbonate is a solid. So KEQ for this is going to be the product. H2O is a pure liquid, so we omit that. CO2 is a gas, so we have to use the partial pressure of CO2, and it's raised to the first power. Calcium chloride is a solution, so we have to use the molar concentration of that. And then calcium carbonate is a pure solid, so omit that. And HCl is a solution, so we'll have to include that and then square it because of the 2. And so this is a hybrid of the KC and the KP, and that's the KEQ that we're going to use here. So this is the scientific method. We take observations of lots of reactions and see, is there a pattern to where these partial reactions end up? And there is a pattern. And that pattern is, the equilibrium constant, or you could call it the law, although nobody calls it the law of equilibrium. So we're going to call it. And then what do we do next? Make a hypothesis and then theory, This would have been hard to make a hypothesis first, Could you have hypothesized that equation? It's kind of a bizarre equation. It turns out that there's another way we can derive this law. We derive the law empirically from observations. The other way we can derive the law from theory. Because the hypothesis is this is all based on thermodynamics and physics. This thermodynamics, delta H, that kind of stuff. And so the other way we could have gotten the law of equilibrium is from theoretical, that is, a thermodynamic analysis, and coming up with equations that way. And that's kind of what the book does here. And so if we look at the book just starts off with a thermodynamic equation for this. This thermodynamic equation comes from a theoretical or more theoretical derivation of this. And so we're talking about Q. We'll talk about Q a little bit later, but it's a A. Do you remember A? A stands for activity. And activity is, let's take a look at activity. Activity was first introduced in chapter 14 at the end here, 14:9. In 14:9, there are 2 concentrations that you dealt with. There's the stoichiometric concentration. The stoichiometric concentration is just what you'd expect. Let's say I had 1 molar sodium chloride. If I had 1 molar sodium chloride, it's a strong electrolyte, so I expect 1 molar of sodium ions and 1 molar of chloride ions. So that gives me a total of 2 molar ions present. That would be the stoichiometric concentration. But there's another concentration called the effective concentration here, effective in quotation marks. The effective concentration is also called the activity, and it's given the symbol little a. And the effective concentration can be different than the stoichiometric concentration because of something called ion pairing. What happens is that sometimes the ions don't completely break free apart from one another. Sometimes there's some interionic attractions that kind of make the ions stick together. Not bond and crystallize and precipitate, but just kind of get stuck. And so they don't act completely independent of one another. And so here's an ion cluster, and you can see the positive ions are kind of clustered around the negative ions, which means they aren't acting independently. And the same thing goes here. You see some ions clustering there. These are ion-ion attractions. They're just kind of sticky. What that means is when we have these ion-ion attractions, it lowers the effective concentration. So let's say you're looking at an acid, and you want the acid to attack base. And so you want the H plus of the hydronium to be free to attack any base it wants. But if the H plus or the hydronium is kind of stuck to something else that doesn't let it go to react, then it's going to be less effective as an acid. And so this brings to mind things like pH. You know, when people think about pH, what's the normal pH range? Do you know? 7 is neutral, so but the pH ranges from what to what usually? 0 to 14. Can it go beyond those? Can it go, let's say, above 14 and below 0? Below 0 would be negative. And you might think no, but it can. It can, because if you're at pH 0 is just 1 molar strong acid. Right, so if you have 1 molar strong acid, it's negative log of 1, it's 0, pH 0. What if you had 6 molar strong acid? Or what if you had 18 molar strong acid? If you had 18 molar strong acid, do you know what the negative log of that? The negative log of that is going to be negative. It's going to give you a negative pH. And at pH 14, you're at 1 molar, like sodium hydroxide. Can you have more than 1 molar? Yeah, what if you had 12 molar sodium hydroxide? That's going to give you a pH higher than 14. And so the general range is between 0 and 14. The general range is between 0 and 14 is because that's where solutions behave more ideal. If you go to very high concentrations, then you have to worry about this kind of non-ideal situation coming up. And so when we do calculations at higher concentrations, we can't use the stoichiometric concentration. So if you had 1 molar acid, that's fine. You probably can deal with that. But if you had 18 molar acid, well, that's a lot. And if you have a lot, then ion pairing is going to be a bigger issue. And you're going to deviate from ideal behavior. And so you can't use the stoichiometric concentration. You have to use the effective concentration of H plus or H3O plus. And so the reason why you didn't do calculations beyond 0 and 14 is because that equation doesn't work. The equation is negative log of H plus. You would have to use what we call activity. Otherwise, your calculation is going to be off. Does that make sense? It's like ideal gas law. The ideal gas law fails at high pressures and low temperatures. Why? Well, it's the same kind of thing, you know. It's the same type of thing where we're looking at the do you remember the Van der Waals equation for calculation of real gases versus ideal gases? The Van der Waals equation had 2 corrections in there. One correction was for molecular attractions. Intermolecular attractions are going to cause the gas to deviate from ideal behavior. And so we look at it like something like propane here, C3H8, has stronger intermolecular attractions than something like helium. So the most ideal gas would be helium. But on this list, the least ideal gas would be C3H8 as far as attractions go. And you can also think of steam. You know, the steam state gas all the way to 0 Kelvin. So if you had steam and you start to cool it down, what happens? What happens at 100 degrees Celsius? It turns into liquid. So the molecules of water stick together. When they stick together, they're no longer gas. And so these are causes for deviations. Well, the same thing happens with solutions as happens with gases. So we can deviate from ideal behavior with solutions. And so, you know, when the solutions aren't very concentrated, they behave ideally. But when solutions become more and more concentrated, then they start to deviate from ideal behavior. And we can see that deviation here in chapter 14. And let me go back to it. So if I have sodium chloride, when you dissolve this in water, it should split up into sodium ions and chloride ions. So it should split up into 2 ions. What we see here is when it's very dilute, it does. This is infinite dilution. But as the solution becomes more and more concentrated, it doesn't quite split apart. And so let's say at 1.0 molal, about 10% of the sodiums and chlorides are clustered together. The rest are independent. And so it should be 2 molal stoichiometric concentration, but the effective concentration is 1.81. And so we have to correct these. The ion pairing gets worse with higher concentrations and gets worse with higher charges. So when we use the theory for chapter 15 to come up with the equilibrium law, we see it should be in terms of concentration. I mean, and not stoichiometric concentration. It should be in terms of effective concentration. And those effective concentrations are activities. Not only that, when we do the equilibrium law, it should be in terms of not the stoichiometric pressure. You know, the stoichiometric pressure is just how many moles of gas you have. It should be done in terms of the effective pressure. The effective pressure is also called the activity. And so at high pressures and high concentrations, we're going to deviate from stoichiometric. And so this is what's going on here. They're using the activities here. So this equation comes from the theory. Yes. I guess it could also come from observations as well. And so we have this equilibrium. Now, the activities, when we're dealing with dilute ones, which in general we are going to be dealing with dilute. We'll go back a little bit more here. Looks like this. The activity of a gas is just equal to its pressure, you know, as long as we are not too high in pressure. The activity of pure solid or liquid is just 1, it doesn't change. The activity of a solution is just equal to its molar concentration. And so, in other words, as long as we're not too concentrated or too high pressure, we can just go ahead and use the concentrations and pressures as I did up there. If we are under,
So, since the activity for pure solids and liquids is equal to 1, is that why we just omit it?
Yeah, that's why I omitted it. We aren't really omitting it. It's really there. It's just
Right.
it's just 1.
Okay.
Activities also have no units. They're dimensionless. So that's why we don't worry about it at all. Okay, so this is it. So how do we get the number? What is the number for these? And so fortunately, other people have measured it. And so we just look it up in a table. In fact, let's look at this table over here. If we look at the middle table, look at the right column here, and look at the heading of the column. K. K is the acid equilibrium constant. This is the ratio of product over reactants. And so we just look it up if we want the K value here. So we just look it up in a table. Let's go ahead and look it up. Because somebody else measured it. You know, if we measure it, we just figure out what the equilibrium, and that's our reaction, and figure out the ratio, just like in the table that I showed earlier. Oh yeah, I forgot. I'm going to post somebody requested the PowerPoint. The book's PowerPoint, so I'm going to post those also on the module. And so here are some K values that we can just look up. Let's take a look at the first reaction here. First reaction is between hydrogen gas and oxygen gas. This is a very downhill reaction. Hydrogen and oxygen are very unstable. Water is very stable, so this is extremely steep downhill. In fact, when we look at the K, I mean, this is huge, 10 to the 83rd. 10 to the 83rd means if I had a trillion, molecules here, all of them are going to be downhill. Out of a trillion, there's probably going to be none uphill. How many? I mean, 10 to the 83, how many is that going to take? Trillions upon trillions upon trillions upon trillions, and then maybe I'll have one. So this would be like a universe of this. Maybe I'll have a couple of molecules uphill. Otherwise, this would be like a Chem 1A stoichiometry problem. Chem 1A stoichiometry is if I have 2 moles of hydrogen and 1 mole of oxygen, I'm going to expect to form 2 moles of water. That's it. And I'll have 0 moles left over. And so we can do this by Chem 1A. And it's hugely downhill. This one's hugely uphill. So if I have calcium carbonate solid going to calcium oxide and CO2, it's 10 to the minus 23. That's like Avogadro's number. 100 trillion, 100, something like that. And so out of 100 trillion, maybe I'll have 1 uphill. It's not much. And so something like this is kind of no reaction. And if you have 1 mole here, then we expect no reaction because no driving force is so steeply uphill. 10 to the minus 23 means it's all product. Very little. And so we'd have Avogadro's numbers worth of reactant and maybe 1 product. But in Chem 1B, though, we're interested in even the minutest amounts. So in Chem 1B, we could calculate, what the ratio would be. Here. And the same thing for this. Even though we expect no reaction in Chem 1A and Chem 1B, we could calculate what the ratio would be. So this would be like limestone statute decomposing into calcium oxide and CO2. This is a redox reaction here. What kind of reaction is this one here? Okay. This one is not redox because calcium stays 2 plus, carbon's plus 4, it stays plus 4, oxygen's minus 2, and it stays minus 2. So the oxidation states don't change. So it's not redox. Is this Bronsted acid base? It's not Bronsted acid. Is this metathesis? Favorable ion combinations? No, there are ions, but you don't see. So it's not Bronsted, it's not redox, it's not metathesis, then it must be Lewis. In fact, this is a Lewis acid base reaction here. And so Lewis acid base reaction is a bit more complicated. We have to look at how the electrons are being shared and that kind of stuff. So draw out the Lewis structure and figure it out. This is, there's some reactions that are quite significant. There's like the top 10. Have you heard this or seen this? The top 10 chemical reactions in modern civilization. You ever heard that? This is one of the top 10 chemical reactions in modern civilization. In fact, there's a big documentary on this particular reaction here. And the documentary, it was like on the Discovery Channel or something like that. And it was about Roman architecture. It was a pretty interesting documentary. You know, first they talked about, you know, the Romans. The Romans had time to experiment in science. You know, they had time to experiment in science because they were farming, and then they rose livestock. And so they weren't out hunting and gathering food all the time. And so they had time to experiment, and then there was plentiful limestone around there. And there's coal. And the coal, they could get very high temperatures. So this reaction doesn't really happen at room temperature, which is 298 Kelvin or 25 degrees C. But at 1200 Kelvin, they could get this reaction to go. Because K changed from 10 to the minus 23 to 1. Well, 1 is about, 1 to 1. So it's not much reaction, but it's a lot more than what was before. And so from this, they could generate this stuff, calcium oxide. Calcium oxide is called quicklime. Calcium oxide was critical for cement. Cement is the glue that holds concrete together. And so from this reaction came the concrete structures in Rome. And the concrete structures in Rome, even today, the concrete is phenomenally strong. When I was working at UCSB, there was a naval researcher. The naval researcher would come to our lab. There's a collaborative thing. He was working on trying to develop better concretes. He worked at the Point Mugu Naval Station, and he was trying to formulate a more resistant concrete, resistant to weathering and erosion, due to the marine environment. And so, but even today, people are still studying Roman concrete because of the characteristics and the properties of it are unmatched. Actually quite a bit better than a lot of other concretes that scientists have been trying to formulate. So anyway, this is a very important reaction for that. Now, at 1.0, it just doesn't seem like, it's going to form all that much product, right? If we need a lot of calcium oxide, how can we generate that? Well, this is, everything is set, like, for example, this is a mix. Solid, pure solid concentration doesn't change, it's 100%. And we have gas here. So probably the best thing to do is use Kp for this, so we can figure out the pressure. So we're going to get some kind of stable pressure of this at the end, and then it's going to stop reacting. But one way to manipulate this is this. We can use something called Le Chatelier's principle. So even though we don't expect much reaction to occur, even at 1200, we can get more reaction to occur. And the way we can get more reaction to occur is to remove the CO2. If we remove the CO2, then what's going to happen is it's going to upset the balance. Let's say the balance is 1, and we start removing the CO2, then what's going to happen is it's going to try to reestablish the balance. And so as the CO2 is being removed, then more calcium carbonate is going to react and then try to get this back in balance. But you keep it constantly in the state of non-equilibrium. You keep constantly removing the CO2, then eventually you can get this to shift all the way, what we call, to the right. That's Le Chatelier's principle. It's a way that, well, the reaction's done, it's not going anywhere. Well, maybe we can make it go a little bit more, or maybe we can make it go a little bit less, depending on how we do it. So, for example, if we don't want this to happen, we can just add CO2. If we add CO2, there's too much CO2 in the balance, and then it has to reestablish that balance by shifting it to the left. And so Le Chatelier's principles is tomorrow's lab. So we're going to take a system that's already balanced. It's got this K, it's got the correct ratio of product to reactant, and we're going to screw it up and see what happens here. Okay, let's look at this one. This one we can't do stoichiometrically. So if we start off with 1 mole of calcium carbonate, we aren't going to form 1 mole of CO2. Just no way. You know, we can't do this stoichiometrically. We have to do this Chem 1b stoichiometrically. Chem 1b stoichiometrically, we'll talk about how to do that later. You know, but for right now, we're just looking at, you know, this equilibrium balance. If we look at K here, this is 3.4, that's 1,000 Kelvin. So this is just not much happening here. 3.4 of 1,000 Kelvin. But this is a redox reaction here. I can tell this is a redox reaction because sulfur is +4 here, sulfur is +6 here. And so there's definitely a change in oxidation state. And in fact, this is just sulfur dioxide being further oxidized to sulfur trioxide. This is an important reaction too. This one in the positive sense, this one in the negative sense, because this one led to acid rain. You know, when people were burning coal, you could have coal contains sulfur, and that sulfur gets burned also. When sulfur burns, it forms sulfur dioxide. And the sulfur dioxide, when it goes into air, gets further oxidized to sulfur trioxide. And then the sulfur trioxide reacts with moisture or rain in air to form sulfuric acid. That would be a Lewis acid-base reaction. And so this caused acid rain. So this is important in that sense. Nowadays, though, you know, coal-fired power plants, you know, so they can generate electricity using coal. The coal-fired power plants are a lot cleaner, you know, because they have scrubbers. The scrubbers, it's not too hard to remove the sulfur dioxide, you know, out of the exhaust gas. So you can scrub that out of there. That goes, you know, technology has changed a lot, you know. Coal is not as polluting as it once was, you know. And so I know there's a big shift to electric vehicles, but, you know, it depends on how the electricity is being produced. You know, if electricity is being produced using coal-fired power plant, is it really, you know, so environmentally friendly? No. Versus, you know, I think if you get some of the older vehicles produce a lot more pollution than newer vehicles do. So maybe we're trying a campaign to reduce the number of older vehicles driving around with less expensive newer vehicles, because newer vehicles technology is much better. The same thing with coal-fired, you know, old technology versus new technology. Big difference. That's why air is so much cleaner, but you know, versus switching entirely to electricity, because when you switch entirely to electricity, you know, how are you generating? But anyway, this one, the same, well, how could we do this? This is 3.4. And so here's this partial reaction. Let's take a look at this one. This is a water gas shift reaction. This is taking like graphite and water. If you take graphite and water, let's say you take a pencil. You take the pencil lead and put it in water. Do you expect it to form much hydrogen gas? Let's say, yeah. I mean, if you did, then don't put your pencils in water, because that would be very dangerous, generating hydrogen gas. But, you know, you wouldn't worry. I wouldn't worry about this. If the pencil fell in the water, I'm not going to be worrying about hydrogen gas being produced, because look at the K value. The K value is 10 to the minus 21, which tells us that there's barely any product forming. It's all reactant here. And so, because this is huge, this is in terms of magnitude, reactant to product ratio. And so this. However, if we heat this up, then yeah, maybe you should worry, you know, because if you drop the pencil into water and then heat it to 1100 Kelvin, well, one thing is water won't last to 1100 Kelvin. You know, 373 Kelvin, water is going to boil. And so we're going to have steam. So if you take steam and then pencil lead, graphite, then you could form some hydrogen. And so this is another way. Well, hydrogen's used as a fuel in fuel cell vehicles. In fuel cell vehicles, they generate electricity by taking this redox reaction. They do a redox reaction like this and then transfer the electrons through the motor. And then, actually, we're out of time. So out of time here, what we're going to do then, tomorrow we're going to do the Le Chatelier's lab. I'm going to post that. It should already be posted on Piazza. And the videos, I'll try to figure out what videos. But tomorrow, can you come prepared for lab? That is, don't wear sandals or open-toe shoes. And then goggles. If you have your own goggles, bring them. If not, then I think there are some pairs still available. Used ones. Yeah, you don't need it for this one.
No.
Okay, but for the future, if you have it, bring it, and I'll talk about it. If you don't have it, it's okay. No, I mean, if you have one, bring it, because, but if you don't, it's not a problem. This first lab is not too involved. What's that? Notebooks?
No, this lecture.
Yeah.
Today.
Yeah. Right. Oh, if you came in after roll, can you